So in the last three examples, we had fractions that had radicals in them, and when we would combine those numbers under the same radical, it ended up reducing to a whole number, which we could then leave in the form it was in, and we didn't need to rationalize. But in these two examples, we actually will end up needing to rationalize these, because if I try to squish this 5 and the 2 together under the same radical, it's not going to reduce. So I'm going to be left with a radical on the bottom. So if you remember from our quadratics unit, when we were left with a square root on the bottom, we had to rationalize. And the way we did that was by multiplying the top and the bottom by the same number. In this case, the square root of 2 on top and bottom. It's just like multiplying by 1, which is why we're allowed to do that. So it's just like multiplying by 1, which makes it okay. I'm not changing the meaning of it by doing that. So square root of 5 times the square root of 2 is the square root of 10, and the square root of 2 times the square root of 2 is the square root of 4. You guys typically would skip over that step, especially after you got more comfortable with rationalizing, and you would just end up here. And this cannot be reduced because you've got one number under a square root and one number not under a square root, and those can't be combined. All right, this example, same thing. You've got a square root on the bottom, and if you try to combine the 2 and the 3 together, they're not going to cancel out. So you need to multiply the top and the bottom by the square root of 3. It gives you 9 square root of 6 over the square root of 9, which is just 3. And then this can be reduced. This 9 and the 3 outside, I can combine both of those because they are both not under a radical. So I end up with the square root, I end up with 3 square root of 6 because 9 over 3 is just 3. All right, so we already know how to rationalize square roots. We already know how to deal with square roots in the denominator. But what about other roots? What about a cube root? So what if we try to approach this the same way that we would approach square roots? Don't write this down yet. Just see what happens here. This is an experiment here. All right, so 3 times the cube root of 4 is just 3 cube root of 4. Okay, that's fine. And then on the bottom, if I combine these, I get cube root of 4 times 4, which is 16. All right. Well, the cube root of 16, that's not a whole number. The cube root of 8 is a whole number, but not the cube root of 16. So I didn't actually end up rationalizing this successfully. So our outcome of our experiment tells us we need to deal with this a little bit differently than how we dealt with square roots. All right, so let's try this again. Well, I mentioned when we just tried that last example that the cube root of 16 doesn't exist, but the cube root of 8 does exist. The cube root of 8 is 2. So basically, I'm striving to get the cube root of 8 in the bottom because I know that 4 goes into 8. So if I can get the cube root of 8 on the bottom, I'm in good shape. That will reduce to be a whole number. All right, so you basically need to say, I want to get the cube root of 8 on the bottom. What do I need to multiply 4 by to get 8? Hopefully you're thinking to yourself, 2. Okay, so I need to multiply the top and the bottom by the same number. So I get 3 cube root 2 on top, and on bottom I get cube root of 4 times 2, which is 8. Ah, this is good. This is ending up how I wanted it to end up. So 3 cube root 2 over the cube root of 8, which is 2, and this is fully rationalized, and I can't reduce it either because 3 and 2 don't have a common factor. All right, so this next example, we need to get a perfect cube in the denominator that 3 goes into. So you want to be either thinking in your head or looking at your exponent chart, thinking about what perfect cube does 3 go into. So I'm thinking 27. Okay, so my goal is to get cube root of 27. I'll just make a little note of that down here. So what do I need to multiply the cube root of 3 by to get the cube root of 27? Well, 3 times 9 gives me 27. So I need to multiply both the top and the bottom by the same thing. This is just like what we did when we were rationalizing fractions with square roots in the denominator. So I end up with 15 cube root 9 up on top. And on bottom, I end up with cube root of 3 times 9, which is cube root of 27. This gives me 15 cube root 9 over the cube root of 27, which is 3. Now this, unlike the last one, can be reduced because 15 over 3 is 5. And so we're left with 5 cube root 9. All right, so in this example, we could think about what would happen if I combined these under the same radical. I would be left with the cube root of 5/2, which that doesn't reduce to anything, so that doesn't really help me out. So I need to be rationalizing this, and I need to come up with the perfect cube, the next perfect cube I can think of that 2 goes into. Okay, so this is like our previous example, cube root of 8. All right, so I need to multiply 2 times what to get 8 on the bottom? Well, 2 times 4 gives me 8, so I need to multiply both the top and the bottom by the cube root of 4. All right, so on top I've got the cube root of 5 times 4, which is the cube root of 20. I just combined those under one radical. And on the bottom, I've got the cube root of 2 times 4, which is 8. And that simplifies. Cube root of 20 up on top, cube root of 8 is 2. And double check the number in the numerator as well. Make sure that it can't be reduced. So is there a perfect cube that goes into 20? Well, my perfect cubes are 1, which I can't really pull a 1 out. That won't make any difference. 2 cubed is 8. 8 doesn't go into that. 3 cubed is 27. That's too big. All right, so I know that this answer is fully reduced. So our last example has a 4th root in the denominator, so our goal now is to get a perfect 4th in the denominator. So if you look at your exponent chart, you'll see that 8 goes into the 4th root, 8 goes into 16, and that's a perfect 4th. So I need to multiply both the top and the bottom by the same number. Well, keep in mind our goal is to get the 4th root of 16. So 8 times 2 is 16, so I need to multiply both the top and the bottom by 2. So I end up with 2, 4th root 2 on top, and then on bottom I end up with the 4th root of 16. And I know that the 4th root of 16 is 2, so my numerator is 2, 4th root 2. My denominator is 2, and notice this one does simplify. I've got 2 2's outside of the radical, and I am allowed to touch them if they're outside of the radical. I am allowed to combine them. Okay, so my final rationalized answer is the 4th root of 2.